Alright, let's make a start. So, today we're going to have a look at how to sketch tan graphs and how to do some of the symmetry properties of the unit circle. So all the stuff involved in flipping things across the unit circle. But okay, first up, tan. So the basic form of tan looks quite similar to your other types of graphs. They're going to have some form of dilation factors out the front and as the n value. There's going to be your horizontal translation, your vertical translation. Works very much the same like other functions do. Tan, however, is a circular function that is a little bit different to sine and cos. In fact, it's significantly different as far as the overall shape. It has these almost like a whole bunch of little cubics are happening in the scenario. And they're all separated by these asymptotes. The reason why it looks so much different to the other circular functions is because tan is specifically sine divided by cos, right? That's actually how you create tan x. That is the ratio. And one of the things that happens whenever you have division in functions is you have the possibility of that division being equal to 0, or the divisor being equal to 0. Whenever you divide by 0, you get a vertical asymptote. And so technically speaking, all of these vertical asymptotes occur when our denominator, cosine, is equal to 0. If it's ever sine divided by cos, then cos is your denominator. If cos goes to 0, you get asymptotes. Otherwise, just some other obvious stuff. Range is going to be all real numbers, so it shoots up to plus and minus infinity. It has these asymptotes at regular intervals. In fact, it still is a periodic function. It just the nature of its period is a little bit different. Firstly, it is calculated by pi divided by n rather than 2 pi divided by n. It's half the period of sine and cos. And the way that it's periodic is between its asymptotes. So all these distances between the asymptotes is the period of that circular function. You'll also note that it has an inflection point at the center of all of the asymptotes. So dead center always is going to be the inflection point. Worth pointing out for anyone who's done calculus, that is not a stationary point of inflection. The gradient there is not 0. This is a more conventional point of inflection, which literally just means where the graph wobbles. So if you were to do derivative equals 0, for those who are familiar with derivative, you're not going to actually find that spot. Okay, dilation factors basically don't matter. Bigger number means it'll be a little bit sharper. It'll be more drastic of a gradient as it inflects upwards. But this only really matters if you sketch two tan graphs on the same axis, like I have here, and the chances of that happening are next to none. I've literally never seen it in any sort of circumstance at all. What is a lot more important is the n value. So in this case, we've got n is 2. That is used in calculating the period of the tan graph. So if we have a look at what it was earlier, it was between plus or minus pi over 2. So that's a total distance of pi. Whereas when you add a 2 in here, you're now between plus minus pi over 4. All right, we've halved that down to just a total distance of pi over 2. I mentioned earlier it's given by pi divided by n, so reminder that n is 2 in this circumstance. It's whatever's directly multiplying the x. So if you were to sub in n equals 2 there, you would get pi over 2, which sure enough is our total distance. Now, why is it half the period of the other circular functions, which are normally 2 pi over n? It's again got to do with the fact that the asymptotes are caused by cosine going to 0. In the case of sine and cos, you go around the unit circle every 2 pi. In doing so, cosine actually goes to 0 twice, if you look at those 2 spots on the unit circle. So for one full cycle of cosine or sine, there are 2 spots on the unit circle where it goes to 0. And so if cos goes to 0 twice, that means you have 2 asymptotes per cycle of the other circular functions, which is why the period is halved. That's just a bit of theory as to why it is the way it is. and could be just another little memory anchor for you to figure out, oh, wait, okay, tan period is a little bit different than sine or cos. You don't actually need to know this, it's more so just another piece of information for you to have to make use of, to memorize things a bit easier. But okay, so some key takeaways. You can pretty much just ignore whatever's at the front. It doesn't really change how you draw the shape. It might change where some of the key features are located, but not how you calculate them. So for all intents and purposes, it doesn't actually really drive decision making. The n value is responsible for the period, and the period is going to be specifically separated by the asymptotes, rather than for sine or cos, where it's going from peak to peak or trough to trough. So if we look at one possible example with just the a and n terms, we got an a value of 3, we got an n value of 2, and we're going to sketch it from negative pi to pi. Before I get into an example, any questions so far? I'll pause for a bit. Okay, cool. So we'll use a framework like this 4-step thing over here for solving this kind of thing. You'll find that most of the time tan will have a symmetrical domain, symmetrical about x equals 0. That just sort of happens to happen. So get used to having these negative and positive parts of a domain. But okay, first thing I like to do is figure out where the asymptotes are. That kind of creates the grid lines that we can use to draw out the curves that we have. So what you're going to do is figure out where the cosine component of tan goes to 0. And you're going to do it over whatever domain you're given. So if you have tan 2x, then the cosine version of that is cos 2x, right? Tan 2x is sine 2x divided by cos 2x, so the cosine component is going to be cos 2x. Literally all you do is you just rewrite tan as cos, and that'll get you your asymptotes. So we just have to solve where cosine 2x is equal to 0 over our domain. We saw earlier that we had our plus minus pi over 2. If I look back here, there's your positive pi over 2, there's your negative pi over 2, and we also have plus minus 3 pi over 2. There's your positive 3 pi over 2, there's your negative 3 pi over 2. Does anyone need a reminder as to how we come about the negative values? If I go too fast, just raise a hand or pop something in chat and I'll be sure to see it. But okay, that gets us our two plus minus values. Reminder that we have cos 2x, so when we grab those two values, you are going to divide everything by 2 at the end. That way you'll get it into the proper domain. And in that way, you'll see that all the values that we have actually fit within negative pi to pi. Whereas if you didn't fix that scaling, if it was still between up to plus minus 3 pi over 2, that's a little bit too big for what we have. Next up, x-intercepts. So the good news is when there's no vertical translations, this is very quick and easy to solve, because the x-intercepts, if we look at tan real quick, they are always the middle of our asymptotes. Always. Unless we shift this thing vertically, up or down, it will always cut over or cross over at that midpoint. So instead of going and setting y equals 0 like you normally do for any x-intercept, a much shorter way to do it is literally just go and look at your asymptotes, dot them all out. So you might dot them all out like this, and then literally just go through each of the middles of those and label those as your x-intercepts. So that's if you do the midpoint form. Otherwise, you could just set tan equal to 0, figure out where tan equals 0, and then that also gets you your x-intercepts. If you need to find endpoints, you just sub in your values. The good news is we actually already did get endpoints. That plus minus pi means that we've already figured out the y values at this for this endpoint domain, for the endpoints of our domain. Which is why we end here and there. Now, once you have all of those key features, you have your asymptotes all drawn out, you have the intercepts all written, you basically just draw cubic shapes. So this is kind of like a cubic. If you have positive tan, it'll be like positive x cubed. It'll go from bottom left up to top right, like it is. Bottom left up to top right. If you have a negative tan, which will look like this, it's like a negative cubic, where it starts top left, ends bottom right. So easiest way I can describe tan is just drawing a bunch of cubics. You can make use of that x cubed looking shape. Anything further to clarify about that example? Awesome. Okay, already talked about reflections there. The one thing I didn't talk about was this kind of reflection, which is pretty rare. I actually don't think I have seen tan with a negative x involved in there, but just in case it does come up for whatever reason, because tan is an odd function, just like the cubic, where it has like if you double reflect it, you get back to where you started. And what I mean by that is putting a reflection vertically would mean, putting this down here and then this up here. Well, technically from this way, this down here, this up here. But flipping horizontally does the exact same thing. Tan of negative x, right? So if you imagine putting this to the left and this to the right, it's actually the exact same shape. So negative tan of x is the same thing as tan of negative x. So if you have both, you actually get back to where you started. Negative tan, negative x, you get back to where you started. There's the three possibilities. The only one that I've ever seen actually show up in a textbook or otherwise, SAC, anything like that, is going to have just a negative out the front. That's true of the other circular functions as well. Yeah, that's about it. Cool. Translation factors. So we can have horizontal translations. Works the exact same way as the other functions. If you have minus a value, it goes right. If you have plus a value, it's going to go left. Now, what I mean by going left or right is simply just going to be all the key values, all the key x coordinates that we found earlier are now going to shift in that direction. So normally we would have it be symmetrical about x equals 0 and it would cut through 0. Now there's an asymptote there instead. So literally all the key features are moving right by pi over 2. Used to have asymptotes at plus minus pi over 2. Now they're at 0 and pi. They're forward by pi over 2. Same thing over here, right? Shifting everything by pi over 3. You're now going to cut at negative pi over 3, cutting at these additional spots. So the only addition that we have to make to our framework is actually, I'll take that back for a second. We don't actually have to make any addition to the framework because you're still solving cosine equals 0. Any horizontal translations or otherwise are actually trapped inside the cosine. And so when you actually solve that, you don't actually have to do anything different. You just solve the cosine that's in front of you. It's a slightly more complicated cosine, yes, but still just solving a cosine. So yeah, I'll take that back, what I said before. You don't actually have to do anything different. There's nothing to think about differently here. What is a little bit more different now is when you have vertical translations. This is where things get a little bit nastier because kind of like how we talked about, well, previous class was talking about the circular function sine and cos sketching. Kind of like how vertical translations were a bit sucky. You have to solve y equals 0 for your x-intercepts. Exact same thing over here. So whenever you have a plus or minus at the end of your function, it's going to be a vertical translation. In this case, we're shifting everything up by 1, which basically means that the inflection point that we had used to be on the x-axis. It's now at y equals 1. What that means for us is that now you'll see that despite having our nice grid of values, these intercepts aren't in the middle of our asymptote anymore. We can't rely on our midpoint equation anymore. We now have to solve for where those are. And yeah, that was just an example of what it looks like when it goes down. So you have a minus a half, which means the inflection point is now at minus a half. we do a slight change to the framework where we start looking at the possibilities of reflection terms, and we want to know, roughly speaking, where to put our inflection point. It's not something you have to label, typically, unless the question tells you to do it. By default, typically what you care about are where are the asymptotes, what are those equations, and where are any intercepts. Those are and endpoints, right? Those are the defaults for tan. So unless your question says otherwise, those are the things that are assumed as necessary. This is more so just so you can get an idea of the shape, right? You don't want to have the inflection points all at different levels. You want to get them on a nice, roughly even spread. Yeah, I don't think there's anything else that's really changed there other than this bit, find the axes intercepts. Before I go on to an example, any questions? Okay, so we've got pretty much everything here actually. We've got a reflection, we've got dilation in here, vertical translation, horizontal translation. One of the first things I'll do in any function is rearrange it so that I can see what all the key features are. Now, that's just more so a good habit. This technically doesn't actually help you solve it any faster, but I would love it if you built the habit of identifying what all the key features are ahead of time, because then even without it gives you another way to figure out if what you've drawn is actually correct. Like if you can't see that this is a shift left by pi over 3, then when you draw your graph and it comes out a certain way, you won't have any idea as to whether you've drawn the right thing. You'll be relying on your ability to do the solving, but you won't have a thing to sort of base it off of. So technically speaking, taking this 3 off of the x doesn't actually help you solve it any faster. It does give you a way to double back and look at it and see, did I actually draw the right thing or not? But okay, that's a good habit to have. So taking any coefficients off of the x reveals what the true horizontal translation is, which is a shift left by pi over 3. Next up, asymptotes. So literally all we're doing is removing, taking tan as its own little thing and then writing cos in that spot instead. So instead of having tan 3x plus pi over 3, we now have cos 3x plus pi over 3. We set that equal to 0 because that's where the denominator equals 0. That's the whole point of getting, well, that's the whole reason why we have those asymptotes. And we're going to solve that over the particular domain that we're given. Solve, 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 solve. It's a bit of a nasty one. I like to do a little bit of a substitution. So I'll take whatever's inside there, replace it with the letter u, fix up the domain a little bit with this substitution. And then now when I get to this stage here, solving this looks a lot nicer than otherwise. Does anyone need me to go into any more detail how we get from complexity to a bit more simplicity?
Chris, could you just explain how you change the domain?
Change domain? Yeah. So it comes from the substitution here. We take whatever's inside the circular function, make that our substitution. The problem is we still got this x domain, but we've now just chucked the letter u inside of the cosine. We need to get this now written in terms of u. And the way to do that is take the x values that you have and put them in the x spot of your substitution. So we have u equals all of this. You put this x value in there, you get this. You put this x value in there, you get this. These become the new upper and lower bound of your domain. Clear enough on that?
Yep, thank you.
Nice. So that gets us to a nice and easier solution there. Where does cos equal 0? Well, it's going to be plus minus pi over 2. I've done a general solution here. That way I can just plug in a bunch of different values of n to get everything within this domain. So you just sub in your n equals 0, n equals 1, n equals minus 1. And for those who haven't done general solution, you can also just get your first two solutions and plus or minus 2 pi from those. That's the exact same thing as what I'm doing here, essentially. These are all u solutions though, so our simplicity does come at a cost, which is now that we have to go back and rearrange these back in terms of x. You kind of have to do this anyway, but it's more so that these are a few extra lines that you otherwise wouldn't be doing, which I think is worth it. But anyway, so now instead of saying u equals all these things, we now say 3x plus pi over 3 equals all those things. Reminder, because that's what u was equal to. We set that at the beginning. Rearrange that, so that just means divide everything by 3 to cancel the 3, and then subtract pi over 3 from everything, and that's going to get you your asymptotes. A lot of stuff going on there, obviously. This is the most complicated you'll ever come across. So if you're following at least vaguely what's going on there, which is replace tan with cos, solve cos equals 0, as long as you get those steps, then you'll be fine for a lot of the questions. But that gets us our asymptotes. Next up, this is not super important. You just want to figure out where your vertical translation is so you can get an idea of where to put your inflection points. We have a plus 2 at the back, which is why our inflection point will now occur at y equals 2, horizontal. Next up, figure out the shape of the graph. I have a whole thing about, you just identify whether you have a negative sign or not. Just treat it like a cubic. If you have a negative at the front, top left, bottom right. If you have nothing out the front, bottom left, top right. Okay. Next up, some intercepts. So intercepts are solved the same way they always are. Y equals 0 for x-intercept, and the x equals 0 for y-intercept. Nothing too special going on there. You just got to be able to solve circular functions when you know the angle. So when you simplify all this down, you need to know what tan of pi is equal to. Cancel that down, ends up equaling 2. Y equals 0, slightly different version. Now you're solving where tan is equal to 1. So again, this is a nice complex thing inside of here, so I'll do a substitution and fix up the domain. Good news is this has already been done. Like, this is the same fix up that we did earlier, so you don't actually have to redo everything here. You can just nice and simply jump into this stage. From there, you need to know where tan is equal to 1, so make use of your unit circle. In fact, do I have a unit circle in here to show? Not really. Just those versions. Point being, tan is equal to 1 at these spots, then you just rearrange to get it back in terms of x. Doing that gave us our intercepts. Next up, if you need to, endpoints. In this case, we've already actually found our endpoints with the asymptotes. So if we have a look back when we did our asymptotes, plus or minus pi over 2, and our domain was plus or minus pi over 2. So technically not really an endpoint, more so an asymptote at the end of the domain. So in fact, yeah, I think this question is ever so slightly incorrect because it has inclusives on that domain, whereas there should technically be exclusives there. So it's actually worth pointing out. But anyway, so here's just a quick summary of what we did. We found vertical asymptotes. That was these. That was step 2. We know where our inflection point is. That's this one here. So you can see it inflects every single time at that spot. And we know that it's going to go from top left down to bottom right because it's a negative, just like a negative cubic would. From here, it's literally just a matter of dot everything out and then draw the shapes. I would go in order. It would be draw your asymptote grid, so these black lines, and if you want to do, you can do the dotted blue line as well, just so you can draw your inflection points at the same level. That one's less important though. Then I would draw the curves, and then wherever the curves ended up cutting, then I would label them. Don't try to label them first because then you'll draw wonky curves trying to get it into the spot. That's it. That's tan. So I'll grab a little screenshot of that summary. And in fact, yeah, it might even be worth putting the whole PDF in there so you can see all the key things in there. There's another section to the lecture, but before I go into that, is there anything I should clarify regarding this? Sketching tan. Okay. And if anything does come up, just let me know. Happy to go back. The next part is on some symmetries. So the unit circle has symmetries involved in it, and if you are very familiar with those, then you can save a lot of time when it comes to solving particular circular functions. The first is that circular functions are periodic. First, we look at sine and cos, which has a period of 2 pi. So basically put, if you know what sine is equal to, then adding 2 pi, or any multiple of 2 pi, to your angle, whatever that angle is, it's the same thing as if you had just gotten back to where you started. The way we solve all of these kinds of questions is with a type of representative unit circle, some reference angle. So you start with the known information. In this case, sine is equal to 0.43. You draw a quick unit circle, and then you put your first quadrant reference. We don't know anything about x, we're not told anything about cos, but we are told that sine is equal to 0.43. From there, all we consider is what is the thing we're trying to evaluate, which in this case is 2 pi plus theta. When you read that, 2 pi plus theta simply now means start at 2 pi and then go forward by theta plus. So we start at 2 pi and we go forward by theta. And sure enough, we get back to the same spot. That's how you read that. Start at whatever this says and then go forward if it's plus or backwards if it's minus. And because we get to the same spot, that means that sine of 2 pi plus theta must therefore stay as 0.43. Same thing for cos, by the way. If we did know cos was 0.43, then you'd still have cos as 0.43 over here as well. For tan, slightly different. We know that tan is periodic with pi instead of 2 pi, so any multiple of pi will get you there. So for instance, if we do tan of pi plus theta, that means start at pi and then add theta, which looks like this. Start at pi and then go forward by an additional theta. From here, we need to consider what quadrant we end up in. Because we've ended up in quadrant 3, both the x and the y are going to go negative, whatever they were. Now, technically speaking, we didn't actually know what x and y were. We just know that y divided by x, that ratio is going to be tan. Point being, if you make both the numerator and denominator of tan negative, it goes right back to being positive, right back to being where it was. So it's going to stay as 0.29. Any questions on those so far? Okay. Next up, we'll do a few more of those pi plus theta. We'll also have a look at some pi minus theta. So here's what they look like mathematically speaking. I personally find that really tough to read. And so little pictures like this tends to be a lot nicer. So let's have a look. We know what sine is. What's pi plus theta for sine? Once again, sine is 0.72, so we write the y value as 0.72. Pi plus theta, start at pi, add theta. That gets us into the third quadrant, which have both negative values. So sine of pi plus theta is therefore the y value at this spot, which must of course therefore be negative of this. Pi minus theta is the opposite direction. So you still start at pi, but because it's minus, you go backwards. That's going to put you in quadrant 2, which therefore means the x's are going to be negative, but the y's are going to be positive. So when you do sine of pi minus theta, you read the y value at this spot, which just so happens to be the same as what it was previously. Same thing for cos and tan, right? Plus theta minus theta puts you in the exact same quadrants as always, but you just read the x values instead for cos, or you read the division of the two for tan. So for cos, 0.84, pi plus theta puts it there, negative. Pi minus theta puts it there, also negative, because it's on the left-hand side. For tan, We already saw pi plus theta, so we can just look at pi minus theta. There's a mismatch of signs now. So that's one way to memorize tan, where it's positive, where it's negative. If there's ever mismatched signs, it will go from being a positive number to a negative number. That, or I know people like using the CAST acronym, which I think goes C-A-S-T, if I recall. It's been a while since I've done that though. Which is C for cos being positive, A for all, S for sine, and then T for tan, and then otherwise everything. I think I've got that somewhat right. Maybe someone can correct me if I got it wrong. Point being, I prefer to look at the where it ends up on the quadrant, and that way you can think about x as being negative or positive, y as being positive or negative, and then you can work from there, because that's a lot more similar to your x and y axis. Any of those I should revise, or are we all good to continue? Alright, easy. Reflections. These look the same way as you've been doing negative angles already, which would be simply you start with wherever your initial value is, and then you flip downwards or upwards. In the case of these kinds of things though, you're always flipping downwards because everything is always going to be a first quadrant thing. I've never seen it where the initial value isn't positive. If it is negative, then well, now you got to start playing around here, but I haven't seen it. Okay, sine is 0.37, that's why we have y as 0.37. Negative theta just means whatever this is, you flip down. Flipping down puts you in the fourth quadrant, where the y values are negative, the x values are positive. So if you're doing sine of a negative theta, you do the y value as negative. Same thing for cos, but because cos remains positive, it's still on the right-hand side, cos of negative theta stays as what it was. Tan, mismatch signs, so it's going to go from being positive to negative. Lastly is the quarter period formulas. So the way these work is a little bit special. It's still something plus or minus theta, which still tells you where to start and which direction to go. But when it's pi over 2 specifically, you also have to invert the direction of the coordinates. So instead of doing xy, you now do yx. So you end up with this sort of like slice of the same quadrant, at least in this case. So pi over 2 minus theta means start at pi over 2, go backwards by theta. You take whatever this coordinate is, you write it backwards. If you ever need a memory anchor to remember what's going on there, just know that this is on the unit circle. Pi over 6 and pi over 3 have this exact same behavior, where they flip the order of their values. So pi over 6 and pi over 3 have that relationship, where if you do pi over 2 minus pi over 6, you do actually get here. You do achieve this flip. So that's one thing that I tend to remember whenever I'm trying to remember, oh, hang on, what's this pi over 2 minus theta nonsense? I remember this this behavior of the unit circle, which for those who are studying circular functions or have done it, I'm hoping you have your unit circle memorized, because as you're probably seeing, it's used in literally everything. But okay, that's why I like to memorize it. The only other nuance there is when you have plus theta. So you're still starting at pi over 2, but when you plus theta, you're now ending up on the second quadrant, which means not only are we flipping the direction of the coordinate, but because you're on this left-hand side, the final x value, which is written as negative y, is going to be negative because it's on the left, right? This is an x coordinate, even though it's written as y. It's only written as y because it used to be a y coordinate over here. Once again, that exists on the unit circle. If you compare these two values, they're identical, with the exception of the fact that this is now negative. So again, another little memory anchor for you. So to evaluate some, cosine is 0.72, put an x as 0.72. What is sine of pi on 2 minus theta? Well, pi on 2 minus theta. You take this, you flip it, you read the y value because it's sine. Same thing, pi over 2 minus theta, whatever you started with. In this case, we had a y value of 0.86. Start it, flip it, and then now you read the x because we're doing cosine at that spot. Plus theta, so in this case, we're starting with the x as 0.86. When you're doing your plus theta, the way I like to do it is in 2 stages. One is to figure out the flip, and then once again you flip over, so whatever this is, you now chuck a negative on that other value. And then yeah, you just read either the x or the y, depending on if you're doing sine or cos at that spot. In this case, we're doing sine, so you read the y. The question will always be written in a way where it won't ask you what this is, because we don't know what that is. It's unknown information to us. And this is just the cos version of that. Tan is worth pointing out because although it's the same thing, it does look a little bit different. And the reason why is because the x and y values aren't known. And so you just, again, have to rely on the division sort of thing. So if tan is 10 over 7, when you flip x and y to be yx, you're now flipping numerator and denominator, because tan is y divided by x. So when you do that flip, you go from 10 over 7 to 7 over 10. Do I need to clarify that one anymore? That's usually a weird one for people. Ah, we're all prodigies. Nice. That or I've done it too many times. Okay. And then if you do your plus theta, that puts you over here. Because we're flipping, we have gone from 10 over 7 to 7 over 10, but because we now have mismatched signs, we go from positive to negative. So we now get negative 7 over 10. Yeah, why not? I think this is the last one. Okay. Pythag identity. So we all know a squared plus b squared equals c squared. Comes from the triangle where c is the hypotenuse, and then a and b are going to be one of those two lengths. If you remember that you can create a triangle within the unit circle, you can also remember that cos and sine are the x and y components of that triangle. So instead of using a, b's, and c's, you can now use sine, cos, and, well, 1, because the hypotenuse is equal to 1 in a unit circle. Simplify that, and you get a nice little ratio that tells you basically, if you know sine, you can always find cos by rearranging. You just put a thing in there, rearrange for cos. So here's a little example. We know sine is 3/5, so we put 3/5 in that spot. Rearrange, rearrange, rearrange. Cos squared. Cos squared theta is the same thing as saying cos all squared, right? So you can square root both sides to cancel that out. That's just a bit of a notation thing that shows up. Problem with square rooting is that you get a plus minus. That's usually why they put this sort of domain involved. This domain here, pi over 2 to pi, tells you that we are in the, wait, what quadrant? Yeah, that's second quadrant. Because pi over 2 is vertically up, pi is on the left-hand side. We're looking at quadrant 2 there, of which only cos being negative makes sense because it's on the left-hand side. So we take the negative version of that. If you then need tan, you can do it by sine divided by cos, once again. 3/5 divided by negative 4/5 minus 3 over 4. Cool. And then here's that laundry list of things that we covered. But fundamentally speaking, this is its own concept. This is its own concept. This, and this you kind of already know from doing a lot of circular function stuff. So even though it looks like there's a lot there, and there is, the individual concepts aren't all that different. So probably the easiest thing I can do about that is chuck the PDF in there, because it'll be easier to reference all the little pictures. Cool. All right. Is there anything in there that I should have a chat about in any more detail? So, for those of us who weren't here on the class 3, But one of the things I'm trialing out now is a breakout rooms sort of thing. So instead of doing questions all as a class and me fielding feedback from it, what I'm going to do is create a bunch of breakout rooms and then visit those rooms one at a time, helping you out through the questions that you're going through. That way, if you've already done all this stuff before, you can just bring new stuff to me. I'm more than happy to have a look at where you're currently at. And then that way, you get at least some personalization out of it. So what I've done is I put a Word doc in the chat there. If you download that, that'll give you access to this book. So that way you can go at your own pace. You can have a look at the particular questions that are assigned, or at least relevant to this information that we just covered. So if you're looking to practice that, that'll be happy there. Otherwise, if you're looking to go in with your own thing and you just want a bit of guidance on that, I'll be there for that as well.